So I'm working on an amplifier here today. This is an Ampeg B15N, classic amp. And like many of these, it has a bad power transformer that I need to pull out. And I can get a socket in all of these other holes to get these back two nuts off, except this one. This hole is not big enough to fit that socket. I don't want to cut up the PCB board because this is a classic amp. And the only other option would be to pull this whole PCB board, and you can sort of see here, like on this tube socket, there's more pins on the other ones, but they're connected soldered to this PCB board. So I'd either have to desolder all of those and undo the wiring and a bunch of the jacks and everything that are in here in order to pull this out, which is quite a bit of time. The other option would be all these tube sockets. The underside, the flange of them is actually riveted to the chassis, so I could drill those rivets out, but then you have to re-rivet them. You could be getting into modifying stuff. Don't really want to have to do that. It's a lot of extra time. So what I figured might be a little bit quicker is to make myself a little wrench extension that can reach in from the side, because I think that there's enough room over here on this side that I will be able to get one in and still move it enough to loosen that nut off. I have a set of other sort of wrench extensions. I forget what they're actually called, but they're like a 90-degree thing. They go on the end of a ratchet, but they don't quite fit in there. Like, you can get it on the nut, but you can't fit your extension in to actually clip it in. So I'm going to hop over to Fusion 360, quickly draw something up that I think will work, taking into account the dimensions I have here to work with, and then I'm just going to cut it out on some 1/8" mild steel. That should be thin enough to fit in there, and hopefully if everything works out right and I calculate correctly dimensionally, we'll be able to get that nut out of there. So this is just one of the many uses if you happen to have an ArcDroid or something like it. One of the great things about having it is to quickly be able to make up specialty tools if you need them. I figured that I've been seeing a lot of posts about new users coming into the ArcDroid because of the price point that this is at and the market it's targeted at. A lot of people are coming in fresh. They've never done CNC plasma before, and the common question is, what settings do I use? What feeds and speeds do I run? I just want to cut some steel. I got some stuff I want to cut out. How do I get started and not make a mess of stuff? So basically what I'm going to cover here is my methodology for figuring out your cut speeds and all of your cut parameters, basically, for any new material you're working with based on your setup. So before we get too far into it, I highly recommend that you go check out my last video where I show you what settings I use for my configuration for the ArcDroid itself. I talk about, setting the jerk down to 1 and my acceleration values to help maximize the ability of this machine to get good quality cuts without all sorts of wibbles and wobbles and everything else. So because of this ARM-based system rather than the sort of other fixed gantry systems, this machine can be a little bit more susceptible to certain wibbles and wobbles if you're pushing it too hard, and because of the tuning in the machine, the acceleration values and such, we have to tailor our settings to work with the ArcDroid. So this is why when you watch videos about maybe the Langmuir systems, their Crossfire machines, or other bigger, more expensive plasma machines, their settings might seem quite a bit different than what we would run with this particular setup. So my basic methodology, one of the key things that you want to keep in mind is that you only want to change one parameter at a time if you can. So depending on what plasma system you're running, what size nozzle, you want to look in your manual, and most manuals will sort of give you a start guide. Now, we're going to do this test here on 18 gauge material. I cut a lot of 18 gauge, I already dialed in settings for it, but I'm going to show you exactly what I did to dial in my settings. So the thing with CNC plasma is that there are faster speeds that you can run where you will have little to no dross, and there'll usually be one or two slower speeds that you can run at where you'll get a better cut quality edge, meaning less bevel, less deviations in it, or little anomalies, and you will still have less dross, or what dross is there knocks off really easily. So there's always going to be that trade-off. You have to decide for your project, do you care about the edges not having much bevel? Because if you don't, then you just run at those higher speeds, get your project done quickly, and move on. And the good thing about running at those higher speeds too, especially on light gauge material, there's going to be way less warpage in it. But if you need those slower speeds to get a good square edge, we need to be able to find that value as well. So one of the mistakes I see a lot of people making is that they do it with straight line cuts. You'll see them, they'll program in a bunch of straight line cuts at different speeds on their material. And that's all well and good, but very few of the cuts that you're going to be doing are just nothing but straight lines. You've got corners in there, you've got different angles, you've got different radiuses and curves. So you will find that if you dial it in for a straight line cut, it may look great, but then when you go to cut out your piece, you've got a bunch of dross, or you've got curves with beveled edges and everything else. So what I highly recommend doing is programming in a slot, and we're going to draw this up right on the ArcDroid. It's fairly easy to do, and all this is a rectangle with a corner radius that is half the width of that rectangle. And the reason for this is it gives us a curved cut, it gives us a straight line, and I found that this is the best way to dial in settings and figure out what it's going to do in an actual real world cut. Okay, so before we do that, if this is your first video that you're watching, just so you know my setup, I'm running an Everlast 82i. This will follow for any plasma machine, especially any that you've got a PT or IPT style torch. But this same basic methodology should work for just about any plasma cutter out there. The only thing that's going to change are some of the number values depending on your cutter. Normally for 18 gauge material, I would run a 0.8 millimeter nozzle, so I can run in the 20 to 30 amp range. Usually I cut that material around 28 amps. For this right now, I have a 0.9 millimeter nozzle in there. That I can run at 30, 31 amps. It'll be fine for our testing here, because I want to also figure out values that are going to work for this 0.9 nozzle, just in case I need to cut some of this material with that nozzle. So we want to remember, we're only going to change one parameter at a time. For Everlast plasma machines, this 82i, it cuts really great at 70 psi, so that's what I'm going to use. I'm going to set the machine at 30 amps with a 0.9 nozzle in there. So that's what we're going to leave the machine set at. The only thing that I'm going to vary is going to be the cut speed itself. Cut height, I know that pretty much all nozzles with this thing, no matter whether I'm cutting at 20 amps or I'm cutting at 60 amps, does great at 1.7 millimeters. That's a value I like. You can pick any value between 1.5 millimeters and 2 millimeters. For our purposes here, it's not going to make a whole lot of difference. I like right square in the middle. 1.7 is a good number for me. That's what I run on everything. So that's what we're going to do here. Okay, so with that done, we're going to go into Simple Trace. And I've got my material here on the bed. And the first thing that I want to do, and one thing I should mention, in case I didn't mention it already, make sure that you have fresh consumables or fairly new consumables in there. Don't use your crudded up old stuff, because again, if you go and try and dial in settings, when you go and switch to new consumables, it's going to be different again, or you could, the worn out consumables can just lead you down a bad path where you can't get any good cuts. So make sure you put fresh consumables in. So I'm going to dial it down here and align it on my material, the torch head here. I'm going to get it placed where I want to start designing. Now this is very important to make this repeatable and easy. We want to make sure we set our 0 point to wherever that corner is going to be. So from there, we're going to go in and we're going to draw a rectangle, and I'm just going to draw it there. And I'm actually going to rotate my origin around so that I'm starting in that upper corner, because then I can just go down and I just have to re-zero every time and we'll be repositioned. So width, I'm going to do 8 millimeters. Width, I'm going to do 25 millimeters. And height, I'm going to do 8 millimeters. And we'll get zoomed in here. And then I want to do a corner radius, since we did 8 millimeters there. We have a slot that can be cut. Very easy. So then I can choose my entry point, and I want to cut this on the inside actually. So we're going to make sure that my entry point is on the inside, and we're going to cut that out. You can set your lead into whatever you want. I usually run 1 millimeter, but for the sake of doing this, let's go up to 3, just for the heck of it. Get more towards the center. Okay, so we've got that all set there. We'll hit enter and back again. Now you can save this if you want. I usually don't, because it's quick and easy to do. You can place this wherever you want. So the good thing about doing it this way is now I can move the torch to anywhere I want on my material, whatever space I want to cut, and if I hit 0, you notice it snaps down to whatever position I want. I don't have to keep redesigning that every time. So go back to there, and I usually like to give it a test run, but I guess first we should go into our tune. My cut height, 1.7 works well, so that's what I'm going to use. Usually pierce height is always between 3 and 3.5 millimeters. That's good. My kerf width, I said that based on my nozzle, I had basically 30% larger than whatever your nozzle orifice size is. That's what I set my kerf to, because that's what I dial my settings in for. Your pierce delay, this really depends on your torch and everything else, so you can set that whatever you want. Off delay, that'll just give a pause after it's done cutting. You can set that to whatever you want. So then our major setting that we were trying to figure out is our feed rate. So like I said before, I've cut quite a bit of this material, around 3,000 millimeters a minute. So why don't we start with that and we'll see what happens. Okay, so we're just going to do a test run here actually first, just to make sure I've got it in the right spot. That looks good. So here we go. Torch is on and run. Okay, so we'll take a look at this, and hopefully this will show up on camera. So those little oddities, you see we did get our slot. Those few little oddities that we've got, especially like down here, that's actually the bit of dross that we have on the back. And you'll see that this actually isn't cutting quite as clean as I've had some other stuff, but there's not a lot on there. You could easily take that off with a flat disc, wouldn't be a big deal. But the thing that you will notice is that on the corners here, you see how we've sort of eaten out a little bit more of a circle, and then it goes into the straight line, and the upper edge of that is actually in a little bit from where the edge of the circle is. So we're not quite getting a line that is dimensionally accurate to the width of this slot as what we'd want. And also, I don't know if you can see it on here, but there is a little bit of a bevel to this edge. Because the arm style system where it has to slow down in order to be able to make this arc, that came out fairly smooth. That's fairly square. On this straight line, though, we're getting a little bit of a bevel there. But overall, you know, cut quality, depending on what you were cutting, it might make sense to cut at that speed. You're not going to have a whole lot of draw, so you can pretty easily knock that off, probably actually even with a wire wheel and or a flap disc, very easily, very quickly. So, you know, that might be okay. For me personally, I'd probably want to dial that in a little bit more if I was going to be running those higher speeds to really figure out what would work a little bit better. So for this next cut, I'm actually going to choose a slower speed because we want to find a good square edge cut, something that's going to leave us with minimal dross but give us a really good quality edge all the way through the cut. The thing is with the ArcDroid is that it cuts really, really well between like 700 and 800 millimeters a minute up to maybe 24 or 2500. That's sort of the optimal range, optimal zone where it seems to perform really well. So if we can pick a nozzle and an amperage with our material that cuts in that range, that's going to give us the best chance at getting a good quality cut. So I'm going to set this up for 1300 millimeters a minute, and we're going to give this another go here. And we'll read the cut and adjust up or down from there. So here we go, torch on and cut. Okay, let's see how we did here. Okay, so you'll notice we did a lot better in terms of our cut quality for our edge. The rounded portions of the corners, they don't look like the upper line going across or the bottom line is blown out any further than what the arc is. And on the back, we'd be looking at this one here. Flip this around. Be looking at that, that slot there. See, we don't have a whole lot of dross, but there is some there. And you just have to take my word for it on the edge quality of the cut. Looks pretty square and pretty smooth. Now, if you look very, very carefully, you will be able to see cut lines where, like sort of where the plasma arc sort of goes along the edge. You see sort of little, I don't know what you'd call them, feather-like lines. The more vertical those are, the better, because the more that they sweep out at the bottom, that means that your arc is starting to lag behind as it cuts through your material. So we want to try to minimize that. So ours look to be pretty straight up and down, and we've got a little bit of dross there. So I'm actually, for this next round, I'm going to dial the speed up a little bit. Normally with a 0.8 nozzle, I would cut at 1300 millimeters a minute for most things, but in this case, because we're using a 0.9 and I've got amperage turned up a few more amps than I normally would, we're going to try going just a little bit faster. So I think this next one we're going to do it at 1400. And I should say that, say you were doing this and you had a bunch of dross and cut quality wasn't great, I wouldn't shy away from, you know, jumping down 300 or 400 millimeters a minute, maybe up to 500 millimeters a minute, just to figure out that zone. If I start getting good cut quality, but I have a lot of dross, or I notice that there's a lot of, the cut almost looks sort of like circles that are connected, I know that the torch is eating away material too quickly. That means that I need to go faster. So don't be scared to move your values up and down 2, 3, 4, 500 millimeters a minute until you start to get in that zone where you've got good cut quality. Then all you have to do is read the amount of dross that you've got from there, and you can adjust up or down. Okay, so machine is set for 1400 millimeters a minute. I just reset my 0 to that new spot and did my test run. Looks good, so let's go for 1400. Okay, so let's take a look at that. And I think we did a little bit better this time. Slightly better, maybe. So our actual dross on back there, a little bit less. That would clean up really, really easily with a flat disc. The cut quality of our edges looks pretty good. I can see a little bit of, some stuff around some of the edges and stuff like that. So for the sake of this, why don't we just try a couple that are a little bit faster and a little bit slower. And one thing I forgot to mention is as you're doing this, you want to make sure you go with a pencil or a marker and mark beside each cut that you do what the cut speed was, because as soon as you start doing a bunch of these, you're going to forget what your settings were at the last one, or your last few, or your first few. Make sure that you grab a marker, mark right next to the cut what your cut speed was. So we're set up at 1600 now. We're just going to run this, and then right after that I'm going to run one at maybe 1000 millimeters a minute, just so we get to see the difference. So here's 1600. Okay, there's our test run. So torch on. This is 1000 millimeters a minute. Okay, so we'll take a look at this. Now I sort of did something not so smart here in that this bottom one here, the slower cut, the dross from that actually bled over into this cut. This was our 1600. But you notice the cut quality on the 1600, very even. Our heat zone, heat affected zone, very even around this one. And the edge quality on that 1600 millimeters a minute is absolutely perfect. Nice square cut. There's no real deviations in it. Came out really nice, and if we look on back, almost no dross for that 1600. There's just a very, very light little lip of it, easily knocked off. In contrast, those big blobs of dross that all came from the 1000 millimeters a minute, you notice we still have a good cut quality for the most part, fairly even shape. Just we've got a lot more dross to have to try and peel off. But there is one anomaly in the cut. We'll see if you can see it here. Right down in there especially, you can see how there was a little bit of a... This actually isn't from a wobble in the machine. This is actually from the plasma arc eating away at the material because it's moving too slowly. Anyway, that is my methodology. Actually, I'm going to grab the grinder and knock this off just to see how easy it comes off, to see if that would work or not. But basically, as far as I'm concerned, if I'm running a 0.9 nozzle on 18 gauge material, say I run out of 0.8s, I can run my 0.9s. I know that 1600 millimeters a minute is going to do it for me. So just give me a second. I'm going to knock that dross off, and we'll take a look underneath and see what that actually looks like. Okay, so I cleaned the front of this off as well, and you can see that both of those cuts, whether it was at 1600 or 1100, came out pretty decently. Not a lot of problems with that. The dross from this slower cut, though, I had to really grind on that to... come on, focus. I had to really grind on that, and you see actually where I almost cut a little bit of a bevel into this material trying to get that heavy dross off there. But you notice the one that we cut at 1600, other than where after it did its lead in, that 90-degree corner, a little bit of something there, but it's small. You can clean that up with a file pretty quick. Other than that, really good cut quality. You see how nice and square the edges are, if you can see that. Probably not going to be able to pick it up because shiny metal now. But you'll just have to take my word for it. The edges of that cut, nice and square. They look really, really good. Dimensionally, looks good. I checked it with the calipers, pretty much bang on for dimensions to what I designed. So that's the setting. Even up here, I buzzed these off real quick. The one that I did at 1400, those cleaned up really quick and easy. That dross was fairly light. But I mean, by far the lightest obviously was at 1600 because there was almost nothing there. So hopefully that makes sense and wasn't really too confusing for you. This probably seems like a little bit more involved process than it really is. Once you get used to doing it this way, it's really quick and easy. What did I do? 1, 2, 3, 4 cuts, and I had my speed dialed in for this 0.9 nozzle one. I haven't really done much with the 0.9 on this 18 gauge material, but now I know 1600 millimeters in a minute works great. So this is a really quick and easy way to do it. Get away from doing the lines. To me, doing the lines at different speeds is just a waste of time, because when you get into a real world cut, that all goes out the window when you've got curves and different features that you need to be dimensionally accurate. The ArcDroid is different, being an ARM system rather than these other gantry style systems. It really doesn't respond the way, it doesn't have the same programming, the same acceleration rates. So we have to pick settings that are going to be more optimal for this machine to get it to cut well. And with that said, you're never going to get the same precision out of this that you're going to get out of one of these $100,000 machines. And I think that's one of the misconceptions that a lot of people have in anything in the fabrication industry, even if it's 3D printing, CNC plasma, or CNC mills. You have to understand that certain machines are at certain price points. Just because a machine is at a lower price point does not mean that it's not useful. You just have to temper your expectations and realize what it's good at, what it's not good at, and that you're not going to be able to run the same settings on something like the ArcDroid that you would on your Maverick CNC table. They're just two completely different machines. They're made to different specifications. They're in much different price ranges. So you wouldn't have that expectation. Anyway, I hope this was useful, and I guess we'll see you all next time.